Okay, so taking a look at example 1, we're presented with two different vector fields, and for each vector field we have to determine whether or not it's conservative. And in the case where the vector field is conservative, we want to find the potential function. Okay, so let's take a look at the first vector field on the left. So here, this is a two-dimensional vector field. Let's label the components P and Q. Okay, so first we need to verify that it's conservative or not. And so going back to the previous page, this is the calculation we need to check. So we take the partial of P with respect to Y and the partial of Q with respect to X. So P sub Y and Q sub X. So we need to calculate these two partial derivatives. Right, so the partial of P with respect to Y. So here we're thinking of X as being constant, so this is just 2X. And then the minus 3 is a constant term, so the derivative makes it go away. Okay, so the partial of P with respect to Y is just 2X. Now the partial of Q with respect to X, so the derivative of X squared is just 2X. We're thinking of Y as being constant, so the derivative of this term is 0. And then again, this is just a constant term, so the derivative of this is equal to 0. Okay, so now looking at these two, P sub Y is equal to Q sub X. So that means that our vector field is conservative. Okay, so now so that's the first step. So now we need to find the potential function. Okay, so again, if you remember, if the gradient of little f is supposed to be equal to the components P and Q, right? So you want f sub x, f sub y is equal to the vector field P comma Q. Then to recover f, I need to integrate P with respect to x. So f of xy is the integral of P with respect to x. Right, so what is P? Is this expression here. So we integrate the expression 2xy minus 3 with respect to x. Okay, so now again, this is a partial integral, so we're thinking of y as being constant. And so what do I get? So I'm integrating with respect to x, right? So you get 2x squared y over 2, and then the antiderivative constant is a constant times x, so you get minus 3x. And then again, this is an indefinite integral, so we need a constant term, but here we're thinking of y as being part of the constant, so the constant term itself should be a function of y. Right, so if you remember, when you're doing indefinite integrals, typically there's a plus c term, and in this case, again, the plus c term is going to actually be a function of y. So this is the plus c term that you typically have when you do indefinite integrals. Okay, so now, so here our function f of xy is still incomplete, right? Because we don't know what this g of y is, and so that's why we also have to calculate this other integral involving q. Okay, so now let's do that. So we integrate q with respect to y. So what is q? Q was x squared plus 4y cubed plus 5. We're integrating with respect to y, so we're thinking of x as being constant. So the antiderivative of x squared would be x squared times y. The antiderivative of 4y cubed would be 4y to the 4th over 4. And the antiderivative of 5 would be 5y. And again, we have a constant term, but because we're thinking of x as being the constant, so the constant term would be a function of x this time. Okay, so again, this h of x represents the plus c term that we typically have for indefinite integrals. Okay, so before I mentioned that we had to calculate these two integrals and compare their terms, right? So you see both of these are supposed to represent our potential function, but they have slightly different terms, right? So we need to look at which terms are the same and which terms are different to figure out what our potential function actually is, right? So let's cancel those out, right? So now notice x squared y and x squared y, so these two terms are the same. Now the remaining terms are different, right? But so again, let's cancel this 4 divided by 4, that cancels out, right? So notice that this y to the 4th plus 5y only depends on y, and so the function of y, the g of y, should actually be this portion of the function here. And similarly, the minus 3x only depends on x, and so the h of x should be the minus 3x. Okay, so now we put everything together, and now we can write down our potential function. So what is it? So this is the same for both, so it has to include the x squared y, has to include these two terms, so plus y to the 4th plus 5y, and it has to include the minus 3x. Okay, so putting everything together, this is our potential function. And as always, you can always check to make sure that these calculations here are correct by checking that the partial of f with respect to x is equal to p, and the partial of y of f with respect to y is equal to q. Right, so if you take the partial of f with respect to x, what do you get? 2xy minus 3, and that's exactly p. And if you take the partial of f with respect to y, you get x squared plus 4y cubed plus 5. X squared plus 4y cubed plus 5. So everything lines up, and we have our potential function. Okay, so that's the first vector field here. And so now let's take a look at part B, so the second vector field. So again, this is our component P, this is our component Q. So what do we have to calculate? We need to calculate the partial of P with respect to Y and the partial of Q with respect to X. So differentiate this with respect to Y. This only depends on X, so the derivative, that goes away. And then here you get the derivative of sine is cosine, so you get x cosine y. And what about the partial of q with respect to x? So this term only depends on y, so that's just a constant. And then the derivative of x squared is 2x. So you get 2x cosine y. And so these two things are kind of similar, but they're not the same. So py is not equal to qx. So f is not conservative. Okay, so we have that the vector field on the left is conservative, but the vector field on the right is not conservative.